Hello everyone, welcome back. So today in this video I'll discuss about the pressure of an ideal gas. So basically we'll keep an ideal gas inside a box, and we will calculate what will be the pressure exerted by the gas molecules on the wall of the container. Also we'll calculate the RMS speed of the molecules inside the box, that what will be their root mean square velocity we'll calculate. So this is from kinetic theory of a gas, and this pressure on the wall of the container has lots of practical applications also. Like suppose a food engineer uh, is keeping some food inside a packet, so they need calculate what will be the gases coming out of that due to fermentation or due to the reactions of other particles or molecules. So whatever the gas will coming out, they will put the pressure on the pack or the box or the container. So it may if the packet will not be very good, so it may leak or it may damage the walls, right? So it has lots of application in practical life. Now in this video we'll calculate the pressure, the derivation for the pressure, and the root mean square velocity. Let's say this is a cubical box. For our to simplify our calculation, we will take, let's say, a cubical box of length L, right? So let's say there are n mole of gas inside this box, and let's say the total number of molecules which are present is capital N, right? So let's say one molecule, first we will calculate we'll consider one molecule which is traveling in, let's say, x direction, will come and hit this shaded wall, and after striking it will go back like this, right? And some assumption will take, like it will not interact with other molecules, because n number of molecules are there and Avogadro's number of molecules. So many molecules, so there will be some interaction between other molecules on their way, and also other chances that they may also change the direction. So we'll consider that it is not interacting with other molecules and it is moving in a straight line and coming back. After striking, it is coming back, and also the collision we will consider as a elastic collision. So these are the assumption we will consider. Now see, if this molecule of mass, its molecular mass, let's say m, it is moving with a direction, let's say x direction, so it's moving with a velocity, let's say vx. So it will have a momentum mvx. We know that momentum is mv, so let's say mvx is the momentum of that single molecule, right? So when it will strike the wall and coming back, let's say its momentum is opposite in direction, minus mvx. So this is your final momentum, this is your initial momentum. Now we'll calculate what is the change in momentum, how much momentum is imparted on the wall. So we can calculate the change in momentum, delta p, right? Delta p is minus mvx, that is the final momentum, minus initial momentum, that is mvx, that is minus 2 mvx. So the magnitude, the amount of momentum that is imparted to the wall, that is your positive quantity, so that will be 2 mvx only, right? Now let's say the molecule starts from, let's say, just from the left hand side, and it is traveling L length, L distance it is covering, because the length of this box is L. So coming here in this wall and striking here and coming back, it is covering how much distance? 2L, right? So it is traveling 2L, and for 2L, let's say it is taking time, let's say delta t amount of time, right? So delta t time it is taking, so you can write that time equal to your distance, that is covering 2L, and your velocity is Vx. It is moving with a velocity Vx. So the distance between the successive collision is 2L, and this is your velocity. Let's say it's taking time delta t, right? So this change in momentum, the momentum, this much of momentum transferred in time, how much time? Delta t time. And after delta t time, again one next collision is happening, and next momentum will be transferred to the wall, right? So we'll write that your rate of change of momentum, that is delta p by delta t, rate of change of momentum, delta p by delta t, we can write t, we can write small t, the time, rate of change of momentum, that is your basically force we are calculating. So delta p by delta t, delta p is your magnitude, will of course write 2 mvx divided by delta t is 2l by bx, 2l by 2 cancelled out. So m, basically we are getting mvx square by l. So this is the change in momentum. This is the change in momentum. Now here we'll calculate what is the pressure on the wall. What is the pressure? So pressure on the wall, pressure, we are interested to calculate pressure. So pressure on the wall P equal to your, this is your basically force, right? Force in x direction basically. So force by area. So area is L square, because length, this is your height, so this one is L square, it is a cube, so one side will be L square area. So F by A, or we can write that F is your this one, right? So mvx square by area is L square, so we can write L, and this is L square, so L cube, or volume basically, right? So this is the pressure by only one molecule on the wall. Now let's say there are molecules which are having lots of molecules, and each one having velocity, let's say n number of molecules I have told. So they are having velocity, each one is moving with a velocity bx1, bx2, bx3, so each one is moving with a different velocity, right? So we can write that this is for only one molecules. Now let's say for n molecules, for n molecules, what we can write? We can write that the pressure will be equal to your m vx1 square plus vx2 square plus plus vxn square divided by LQ, or your volume, right? So now what I can write, this one, let's say I'll write one average velocity instead of writing all this velocity, because I'll write one average velocity, right? So average velocity, I'll write that your pressure will become m Vx. So let's say Vx1, Vx2, Vxn. So divided by n, I'll write average, that Vx square average by LQ. So this is the velocities of your average velocity of n molecules, right? And also for n molecules you can write n here, it's n molecules, so n you can write, fine, n molecules, each one having velocity vx1 vx2 like that. Now what I'll do, this Vx average square, now let's say only one direction, now it will also strike the y direction, it can, there are chances that it can strike on the z direction also. So Vx square, let's say Vx, it will have velocity in all direction, so Vx square average equal to V y square average equal to Vz square average, or we can write that Vx square average equal to 1 by 3 V square average. V is the, V consists of Vx, Vy and Vz, right? So this one we can write that it is one third of n m V square average, right? V square we can write average, a b z like that. V square average, bar means average, here you can write average, right, by LQ. LQ is the basically volume. So n by b, n is the total number of molecules, this is total number of molecules present in this box, so the total number of molecules so n by LQ is number of molecules per unit volume. So basically we can write that pressure equal to n by LQ is 1 by third n, small n is the number of molecules per unit volume, n by LQ, and small m is the mass of the one molecule, and this is V square average. I hope this is clear. This is your pressure on the wall, this is pressure on the wall, 1 upon 3 n m V square average. N is the number of mole per unit volume, m is the mass of one molecule, and V square average is the velocity square average. Now we'll write this, get an expression in terms of RMS velocity. What is RMS velocity? RMS velocity is root mean square velocity. That means you can say, suppose there are 4 velocities or 4 numbers, 1 2 3 4. If I'll ask what is the average of this 1 2 3 4, so we'll say this plus this by 4, whatever the result you will get, this is your average or mean. Now if I'll say what is the root mean square of this number, so you'll say 1 square plus 2 square plus 3 square plus 4 square by 4 root over. So the result whatever you will get, the RMS whatever you will get will be slightly greater, you can calculate that. So this is your RMS, root mean square number, this is your average, right? So average and root mean square both are slightly different and close to average value. Our root mean square value is close to average value but greater than average, it will be greater than average value. So we'll calculate the RMS value in terms of RMS value. So we can do that, we'll write this, that V square average root over is V RMS, V root mean square, or we can write V square average equal to V RMS square. Alright, so this equation we can write in this way, that pressure equal to 1 upon 3 n m small m n m V RMS square, right? Now we'll find out a relationship of RMS, root mean square velocity. Okay, so this is velocity. So RMS velocity will find out because we have kept one ideal gas inside this box. So what we'll do, your ideal gas equation will use. So from ideal gas equation, from ideal gas equation, what you can write? PV equal to mu RT. Why I have used mu? Mu is the number of mole, because N and N you will get confused, so I am using mu RT. N is the number of mole per unit volume, remember, right? So N we have, small n we have used N, capital N by LQ. Now we'll replace this P here and we'll find out a relationship of V Rms. So pressure we can write here, this is 1 by 3 N M V Rms square. This is your PV. V is, this is volume, right? So if you will confuse, I can write this is LQ also, or if you are not confused, remember this V is volume, this V is volume, right? This V is volume. PV, P is this one we are putting from here, and V is this one, so equal to mu RT. Now we are interested to find V Rms. So V is the velocity, RMS speed. So V Rms speed, V Rms square equal to your mu RT. 3 will be multiplied, so 3 mu RT divided by Nm. Small m is the molecular mass of that atom. Small n is the, here we have used number of N by LQ, N by V, and mu is the number of mole. So just we'll replace these numbers and we'll get one equation like 3. Mu is the number of mole. So number of mole we can write that it is N, total number of atom molecules inside this box, divided by Avogadro's number. Number of mole equal to N, total number of molecules, divided by Avogadro's number. Avogadro's number means 1 mole. So suppose 5 mole gas is there total. So this is N is the 5 mole, 5 into Avogadro's number divided by Avogadro's number. So mu is the number of mole, that means 5 will come out, right? So N by Na, Na is the Avogadro's number, N is the total number. So N by N is mu. So mu I'll write N by Na. R is the gas constant, T is the temperature, N, small n is what? Small is the number of, we have used just here, that is capital N divided by LQ, volume. And okay, this B is there, this is also volume, and M is the mass of one atom, and B is the volume. So LQ and volume cancelled out, N and N cancel, Na will come down. So what you will get finally you will get V Rms square root, it is a square, so now it will become square root. So V Rms equal to, this is your 3 RT, R is the gas constant, and this is NaM. In the denominator, mass into Avogadro's number, mass of one molecule multiplied by Avogadro's number is your molar mass. So molar mass, capital M I will use, where in bracket you can write M into Na is capital M, which is the molar mass, right? So this is your V Rms. V root means square velocity. V Rms is 3 RT upon M. V Rms is 3 RT upon M, right? So I think it's clear, and this is very important. This V root mean square velocity, every time question comes from in different competitive examination, most probable velocity also from Maxwell distribution curve also comes. That one we will discuss later on in another video. And very important, this formula pressure, right? And you can convert this N in N by V M also in different forms, right? Sometimes volume is given, sometimes number of molecules will be given, and pressure will be asked. So this equation you have to convert in different way. You can convert, right? Like I converted mu to N by Na, your n to n by LQ or n by V, whatever you write. So you can convert this terms. Remember one thing, n is small n is where whatever we have used here is capital N by LQ, and capital N is total number of molecules inside this box, and Na we have used, that is your Avogadro's number, that is your Avogadro's number. So N by Na is your number of moles, and small n is number of molecules per unit volume, right? So this is your V Rms. So from here you can calculate the energy, kinetic energy of one molecule. So you can calculate kinetic energy. How will you calculate? So kinetic energy also you can calculate. Kinetic energy, we know that it is half mv square. So as we are calculating RMS speed, a molecule will move with a root mean square speed. So we can say kinetic energy, average kinetic energy of a molecule is half m is the mass of that molecule, and V Rms square, half mv square. So V Rms, you can use this formula from V Rms square. So you can write half m V Rms square is your 3RT by capital M. Small and capital M are different. It's mass of one molecule. M is the m into Na, that is mass into Avogadro's number, right? And so you can write that your kinetic energy, average kinetic energy, is coming as, it's a very important formula, and also very surprising formula that come up, and lots of research then was there on this formula, on this concept. So kinetic energy, average kinetic energy equal to 3 upon 2 your 3 upon 2 m, right, m r t, and capital M is m into Na, mass of one molecule into Avogadro's number. So mass gets cancelled, and R by Na is a constant. Na is a Avogadro's number, 6.02 into 10 to the power 23 numbers, and R is the gas constant, 8.31 joule per mole per Kelvin. So what we are getting, this R by Na will introduce another constant, that is called Boltzmann constant, right? 1.38 into 10 to the power 20 minus 23. So this one will be your 3 by 2 K Boltzmann constant KBT. That means average energy associated with one, average kinetic energy is associated with one molecule is 3 kBT. That means it's a constant. 3 by 2 is a constant, kb is a constant, and T, that means energy of a molecule depends only on the temperature. So if we are measuring the temperature of the molecule, that means you are measuring also the what are the average energy of the molecule also you are measuring. That's a very interesting result, and when from the equipartition of energy we will discuss in the next videos that if an atom is a monoatomic one, then it will have 3 degrees of freedom, and each degree of freedom will be associated with half k beta t, right? 3 k beta t, 3 kt. So each degree of freedom will be associated with a energy half kt, right? This is a very interesting result. So average energy come up, kinetic energy came up as 3 by 2 kt for one molecule, and for 1 degree of freedom it will be half kt, so it will be 3 by 2 kt for all the 3 degrees of freedom, if we'll say, right? Okay, so this is the kinetic energy average. So in the next video I'll discuss about equipartition energy, also if possible Maxwell distribution, most probable velocity, that is from Maxwell probability distribution, and mean free path also left in this chapter, and we'll also solve some problems. So thank you for watching the video. If you find any doubts, you can write in the comment box so that I'll go through it, and if possible I'll make another video clarifying your doubts. Thank you for watching the video. See you in another one. Bye bye.